All right. Today we are introducing the foundational idea of calculus, really, the limit. And so we're going to start with the definition. The definition is, suppose f of x is defined when x is near a, some number a. We write that the limit as, we say the limit of f of x as x approaches a is L. That's how this is read. If we can make the value of the function f of x arbitrarily close to L by taking x value to be sufficiently close to a, so either above or below a, but not equal to a. So if there's some small boundary around a on either side, where any x value within that, the value of the function will be as close to L as we want it to be. Then we would say the limit of the function f of x as x approaches a is L. We may also write it like this: f of x approaches L as x approaches a. This is another notation that we might use. For example, we might want to look at what is the limit as x approaches 1 of the function x minus 1 over x squared minus 1. And to illustrate that, let's look at what a graph of that would look like. And so by looking at the graph of the function x minus 1 over x squared minus 1, we can see as x kind of approaches 1 from either side, it looks like the function is approaching about 1/2. And so I'll say is approximately equal to 1/2. That seems to be what happens to this function. Of course, we know if we plugged the value 1 into this function, we would actually get an undefined value, right? The function is not defined at 1. But remember, the definition of the limit isn't that the function is close to, say, 1/2 here when x equals 1, but only when x is close to 1, but not equal to it. Here's another example. We want to estimate the value of this limit, the limit as t approaches 0 of the square root of t squared plus 9 minus, here's another example. We want to estimate the value of the limit as t approaches 0 of the square root t squared plus 9 minus 3 over t squared. So again, let's look at a graph of this and see if that can help us make this estimation. So here it seems like as x gets close to 0, the function looks like it's getting close-ish to, I'm going to estimate 0.1, 0.2 is up there, so that's about 0.16, 6. You know what? If there's 3's involved, there's 9's involved. I'm gonna guess it's gonna be 0.16 repeating. That would be 1/3 divided by 2, or 1/6. Is it 1/6? So this is the idea. And this isn't meant to. We're not solving this. We're just estimating it. And it seems like this function, of course, is not defined when t equals 0, because you're dividing by 0, which is, as you know, the biggest no-no in math. But it looks like the function approaches the value of 1/6. Here's another one. We want to estimate the limit as x approaches 0 of the function sine of x divided by x, and we'll estimate it by here. Let's try plugging in some values. So let's just plug in the values -0.1, -0.01, and -0.001 into this function, and then we'll do the positive values and just see what we get, and I'll evaluate those. So when you evaluate this in a calculator, what I'm getting for negative 0.1, I'm getting 0.99833. For negative 0.01, I'm getting 0.99998. For negative 0.001, it comes out to be 1. I'm thinking that's rounded off, and I get the same values in the opposite order when I put in the positives. And if we look at the graph of this, this should come as no surprise. You can see as the x values get close to 0 from either side, the function is approaching, looks like, the value 1. Even though, as we've said before, in the other examples, the function is not actually defined when x equals 0. But the limit is defined, because limit is the value that the function gets close to when x gets close to 0. Doesn't mean the function ever reaches the value 1, although this was, I'm sure, just due to rounding, rounded to when you round it off to 5 decimal places, I'm sure it comes to 1, but my guess is it's 0.9999999 something, and then it's something that's not a 9 eventually. All right. Here's an example of a limit that actually doesn't exist. The limit of this function h of t, where as t approaches 0, and I'm defining h of t to be just equal to the value 0 for any negative t, and h of t is equal to 1 for any for 0 or any positive t value. If we were to graph it, it would look like this. This is a sketch of this this function, and so you can see when t is negative as it approaches 0, as t approaches 0, the function is approaching. It's approaching, and it is equal to 0 that whole time. But as x approaches 0 from the positive direction, it's approaching, the function is approaching the value 1. And so the limit does not exist because there's not one single value that we can get the function arbitrarily close to from either direction. Its limit, and we'll talk about these next, this left side limit and this right side limit. So this is an example of a function that has no limit. Okay, so this is the definition of a left-hand limit. So we'll say that we write it like this, and we say that the left-hand limit of f of x as x approaches a is equal to L. All right, that's how that's read. And you notice that little minus sign is this little superscript after the a. If we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to, but less than a. And we'll say that we'll write it like this when we talk about the right-hand limit of f of x as x approaches a. And just notice that we put the little plus as a superscript instead of the minus. So in both of these cases, it's like, let's try to illustrate it. You have some axes, and here's the function L. You know what I'll do? I'll put in the left hand. I'll just illustrate the left hand limit as. So what I've illustrated here is the left hand limit of f of x as x approaches a is L. Right? You can see that as the function approaches from the left hand side, that the function value gets close to L, but it's not true from the right hand side. This is the epsilon delta definition of a limit. It's a more technical definition, and it's good to know about this. So this is it's an alternative definition of a limit. I'm going to read it out for you. So if f is defined on an open interval that contains a, and open interval meaning it's up, not including the bound, the lower bound and the upper bound of the interval, except possibly at a. So the function doesn't have to be defined at a. We say that the limit of the function f of x as x approaches a is the value L, and we write it like this, the same way we wrote before, if, and this is the epsilon delta definition. For any epsilon greater than 0, epsilon's like a small number, like a very, very small number. Any epsilon you pick. There exists some delta greater than 0, such that as long as the absolute value x minus a is between 0 and delta, well, absolute value x minus a, as long as it's less than delta, it's going to be greater than 0 as long as x isn't a. So this is saying as long as x is within delta of a, it will imply that the function value is within epsilon of L. And this is kind of an illustration to hopefully kind of give you some intuition about what this is talking about. The idea is like, so somebody says, I want the function to be no further away from L than like epsilon away, like a very small amount. So what we're saying is like for any value of the x that's within this interval, we can find some delta. As long as it's within that interval, then the function value is going to be within L plus or minus epsilon. As long as sort of one person demands that it be within epsilon, as long as we can respond by finding a delta, and the delta can depend on epsilon. It can be a function of epsilon. In fact, it usually will be. As long as that can be achieved, that satisfies the definition, and then L is the limit of the function. Here's an example. I want to prove using this epsilon delta definition that the limit as x approaches 3 of the function 4x minus 5 is 7. So here I'm kind of cheating, and I already know that the limit is 7, and I want to prove it using the epsilon delta definition. So the idea is that we want, as long as x minus 3, the absolute value of x minus 3 is less than delta, we want that to imply that 4x, the absolute value of 4x minus 5 minus 7 is less than epsilon. So what we're going to do is we're going to start with we're going to start with what our goal is, and we're going to kind of work backwards to get this left-hand side, or something that looks like the left-hand side. So what we're going to do is we're going to kind of cheat and work back. Well, I don't know if cheat is the right word, but this is the way we do it. All right, so let's take a look at this left-hand, or this right-hand side, sorry, and we're going to simplify it. So this 4x minus 5 minus 7 is going to be 4x, the absolute value of 4x minus 12 less than epsilon. And actually, if you see here, this is the 4 is a common factor. I'm going to factor out the 4, and I'm going to get 4 outside the absolute value x minus 3 less than epsilon. And then if I divide both sides by 4, which is positive, so it's not going to change the inequality sign, you get epsilon over 4. And then I've achieved, this is my left-hand side. But it doesn't have a delta, it has epsilon over 4, so I can just say, given epsilon greater than 0, any epsilon positive, if you just let delta be epsilon over 4, then if x minus 3, as long as the absolute value of x minus 3 is less than delta, which is epsilon over 4, this is going to imply, eventually, you're just going to go through, you can get back the 4x minus 5, absolute value 4x minus 5 minus 7 will be less than epsilon, because you would be able to just kind of work backwards up the chain, because each of these statements is completely equivalent to each other. So now if this is a linear function, if you had something that was a little funkier, you would have to probably take cases where what if x is like greater than 3 or x was a little bit less than 3, and figure out how to handle these absolute value signs. But this is the general idea of these epsilon delta proofs of a limit. Here's another example I want to look at. I want to prove that the right-hand limit of, as x approaches 0, of square root x is equal to 0. And so I want to, again, what I want to do is I want the statement that as long as the absolute value of x minus 0 is less than delta, I want that to imply that the absolute value of square root x minus 0 is less than epsilon. But notice that since I'm only looking at a right-hand limit, I know that x is going to be greater than 0 always. Because x is always greater than 0, then I can clear away some of the absolute value signs. And so these two statements simplify to being, as long as x is less than delta, I want that to imply that square root x is less than epsilon. So I'm going to do the same thing I did before. I'm going to take the right-hand side, I'm going to try to massage it to get the left-hand side. So I'm going to square both sides. I'll have x less than epsilon squared. Oops. Epsilon squared. And I've got it. I'm going to, given epsilon greater than 0, we're going to let delta just equal epsilon squared. And so as long as x minus 0 is less than delta, that implies, well, that's the same as x is less than epsilon squared, and that means the square root of x is less than epsilon, which is the same as, implies the absolute value square root of x minus 0 is less than epsilon. These are equivalent statements, but this is the idea for this epsilon delta proof for the square root of x function. We were able to put absolute value signs, stick them on, not worry about squaring and square roots, because we're only dealing with positive x values. And so again, we didn't have to worry about the sign, the plus or the minus, and any of that business. But anyway, yeah. So these are the ideas of limits and one-sided limits. Okay.